We'll be starting with this first session in the afternoon. This is the Preparing for Blue Water session, and we have three very interesting talks. The first one is by Yanhua. Yanhua-san. He'll be presenting uGNI-based Charm++ runtime. Yanhua is a PhD candidate in the Parallel Programming Laboratory.
Good afternoon, everyone. Welcome back. I'm Yanhua. I'll present uGNI-based Charm runtime for Cray Gemini Interconnect. I did this work since last June. That time I didn't expect this is something related to blue water. So this is the cooperation work between University of Illinois, Cray Company, and Oak Ridge National Labs. So as we know, modern interconnects are becoming very complex. The supercomputers from different companies like IBM's and Cray's have quite different interconnect. So even for the same companies, their supercomputers from different generations also have a quite different interconnect, like Cray XT5, XE6, they have C-stars, and Gemini Interconnect. So it's quite challenging to obtain good performance for applications with various communication patterns. So that's for the hardware. On the program, on the other side, so there are multiple programming models and language, as Robert said. So traditionally, MPI carried the way, but now it's no longer. We have like UPC, Core Array Fortune, and also companies are very active to the programming models, Chapel, X10 from IBM, and also we have a Charm. So here the problem is how to attain good performance for applications in alternative models for different interconnects and different hardware supercomputers. So in this talk, I'll focus on exploiting the performance of Charm programming models on Gemini Interconnect. So Gemini Interconnect is installed for the Cray new computers, XE6, XK6. So that's the interconnect for the blue waters and also for the Titan at Oak Ridge. So first you may ask, so why not to use MPI-based Charm? As we all know, we have the MPI Charm which can run universally on every machine. So there's when there's a MPI library running there, well, it works, but usually that's not the best one in the aspect of the performance. So there are two reasons. First, so MPI has have been developed for many years. So it has a rich set of functions and features. Usually every feature will lead to some extra overhead. However, not every feature is required into Charm. Like in MPI, message deliver is in order, but this is not required in Charm. So we try to avoid this unnecessary overhead by doing some native porting for Charm. The other side is the data interaction pattern in Charm is quite different from the MPI. In MPI, when we transfer a data, it requires both sender side and receiver side involvement. Sender side need to call MPI send, and receiver side need to call MPI receive. But in Charm, only the sender side explicitly calls the entry function call, but receiver side there's a Charm scaler which is responsible for message-driven and function execution. So to have a first sense of the performance, we did a Pingpong benchmark for the raw uGNI machine layer and the MPI-based Charm performance. This figure shows the one-way latency of the Pingpong benchmark for different sizes of message. So we can see for the messages which are smaller than 4K bytes. The gap between the Gemini Interconnect and the MPI-based Charm, the gap is very big. And also, on the other side, for most applications, especially for very fine-grained decomposition applications, the message is around a few kilobytes or even smaller. So this big difference gap will kill the application performance. So the gap is due to 2 reasons. First, we can see the middle curve of the pink curve. So that represents the performance of pure MPI. So even the pure MPI performance is kind of worse than the Gemini performance. And also, based on the MPI layer, the Charm brings its own overhead. So in this talk, I'll first briefly talk about the Gemini Interconnect and its lower level communication library, uGNI, and then I'll discuss about the uGNI-based Charm design. And then next, I'll talk about one optimization we applied to improve performance, and then the performance result of using a few micro benchmark and 2 applications will be discussed at the end. So Gemini Interconnect is Cray's newest interconnect upgraded from its previous C-star interconnect. It has quite low latency. On a quiet interconnect, 1 hop latency is around 700 nanoseconds, and when you increase 1 hop, it's usually 100 nanosecond increase. And also the bandwidth is quite high. It's like 8 gigabytes second per link. Usually for the 3D tours, there are 4 links for the XZ dimension, and then another 2 links for the Y dimension. It's also claimed to scale to 100,000 nodes. So to have a concept like the biggest machine in US currently, the Titan, only has 19,000 nodes, and Blue Water has like 20,000 nodes. So this hardware also provides the support for the one-sided communication. So this feature is quite friendly for the PGAS language, but it's not perfect for the message passing libraries. So in the hardware, it provides 2 function units to transfer data, which called fast memory access and a block transfer engine. Depends on the message size, these 2 function units will be used. For the fast memory access, when the data is transferred, the CPU will be involved to copy data from the memory to the FMA window. And for the block transfer engine, the startup time to transfer data takes longer, but once the startup is done, so it can transfer very huge amount of data. So to utilize the Gemini Interconnect, 2 libraries are provided to the developers. The first one is distributed memory application, which is also called DMAP. That the programming style is more like you have the barriers, and between these barriers, you can access the global memory by using get output functions. So this function, this library is mainly used for the PGAS language programming. The other one is the user-level generic network interface, which is called uGNI. This library is what the MPI implementation is based on. Also, we use this library as the lower-level communication library for our charm porting. There are many functions in the uGNI APIs, but here we only cover these 3 most important ones, which are memory registration. So in order to transfer any data, the memory for that message must be registered That means that memory must be pinned to the physical memory so that that memory can be accessed by the network card. When the memory is registered for the both sender side and the receiver side, the FMA and the BTE transaction is posted to the uGNI library. That library will be responsible to transfer the data. When the transaction is done, so there will be event notification to the completion queue. By putting this completion queue, the users can know, okay, this transaction ended done. And so the data on the receiver side can be delivered to the up-level runtime, and on the sender side, the data can be freed. FMA is the fast memory access. BTE is the block transfer engine. So in order to port Charm to a new machine layer with a specific interconnect, Charm provides a minimum set of interface which must be implemented to port Charm. So we call it lower level runtime system, also called like LRTS. So there are like 8 or 10 functions which are required to implement, like topology-aware stuff, the NUMA-aware stuff, things. But these 3 functions are extremely required to implement a minimum set of LRTS. So the first one is the LRTS init. So here we will like get the process ranks, process the size of processes, and also do the basic initialization. Like in MPI, we will call MPI initialize, and then something else for Charm specific. Once the initialization is done, so LRTS sync sender is responsible for deliver Charm message from the upper level side to the network. So sometimes message is not directly sent to network, but it will be buffered into. So once it's buffered, this advanced communication will responsible to send this buffered message, and also this function will pull in the network to get the message from the network. So according to what we discussed previously, so in the Charm, in order to send a message, on the sender side, the message is allocated for some memory, and this memory is registered to the network. And with all of these informations, memory address, memory handler, and the size of message, a small control message is sent to the receiver side. Once this small control message arrives at the receiver side will allocate the corresponding size of memory, and then register this memory, issue a FMA or RDMA get transaction. So once this transaction is done, on the receiver side, the message is delivered to the Charm, and a small ARC message is sent back to the sender side, so that the sender side will deregister this memory and also free the memory. So in this figure, we can say, in order to transfer one message, it actually involves the 3 message transaction. With the message size increasing, the FMA, RDMA get transaction will dominate the total time. Like I said, it involves 3 triple time latency. But this is okay for the large message, which is maybe like larger than 10 kilobytes or even larger. However, it's not good for small message. So like a small message, the actually latency is 1 microsecond. When you involve the 3 latency, it will be 3 or 4 or even more. So uGNI provides another library called the Small Message Protocol. So in this protocol, you don't have to register the memory for that buffer. You just directly send this message like the way we use MPI send this message to some processor without knowing the receiver size memory address. Currently, the maximum small message size is 1024 bytes. Of course, this size can be adjusted. However, when you have a bigger value for this small message, that means you you need a large mailbox. Mailbox is like a chunk of memory which is used to hold the small messages. Actually, that's the way uGNI just copies that small message to this mailbox, and then uGNI library will be deliver this message to network. So when you increase this small message size, the total memory required will be also increased. Also, in order to use this small message protocol, you have to set up the connection with all of your pairs, so that when the data is transferred, the connection is already set up. So this figure evaluates the performance of this design. So we can see with this small message transfer, the middle curve of the pink color is the uGNI-based charm, and the blue one is MPI-based charm. When the message size is smaller than 1 kilobytes, our uGNI-based charm performance is very close to the pure uGNI performance. However, when the message is larger than the 1 kilobytes, the performance gap is still quite high. So as I said, here we involve 3 message latency and also the pre-setup for the message on the both sender side and the receiver side. And even uGNI, the memory registration and memory deregistration is very costly, especially when you already register some memory, you continue register something, the cost will be increased. So different from MPI, the user will explicitly allocate the memory and then pass this memory pointer to the MPI library. In Charm, when you can allocate a message, you directly call Charm allocate a message. So this memory will be controlled, totally controlled by the Charm runtime system. So here we can have the idea. This Charm is totally control all of the memory allocation and deallocation. So at the beginning, we can pre-register a big chunk of memory, like hundreds of megabytes. And every time when we call a memory allocate, we just go to this memory pool instead of go to GNU alloc or something. And with this memory is used up. Next time when we allocate, we continue allocate the big chunks instead of smaller ones. And so since then, every memory allocation and deallocation will go to this memory pool instead of other allocs. So with this mem pool idea, we can see the blue ones is the optimize performance of uGNI implementation. The top pink ones is the original design. And we can see the for the 1 kilobyte message, the latency is decreased from like 10 microsecond to the 5 microsecond. So combining the small messages and the large ones, we can see comparing with the MPI-based Charm, both the smaller message and the large message, the uGNI-based Charm has a big one. Also, this figure shows the bandwidth achieved by MPI-based Charm and uGNI-based Charm. We can see to achieve the same bandwidth, in MPI we have to use much larger message. In Charm, the message size can be like 1/8 of the MPI messages. And the peak performance, like using 1 megabyte message, is like 5.5 gigabytes per second. We test our implementation in NQueen's problem. NQueen's problem is a very classic state space search problem. It's very fine-grained. Each object only contains like hundreds of bytes data. So for this quite fine-grained problems, for the 17 Queen's problem, with the uGNI-based Charm, we can scale up to 4K. However, for the MPI, it only scales up to 512. After that, because of the a very high overhead of the MPI library and Charm library. It stopped scaling. Most of that work was done last year. This year, we pushed a lot on the NAMD performance. So recently, we submitted a SC paper about NAMD performance. So with some other optimization, we can scale the NAMD 100 million item to the full Titan machine, which is around 300,000 cores. And comparing the old Jaguar, the time step is like 26 milliseconds. Currently, with Titan, we can achieve the 13 milliseconds. So with MPI-based Charm, that is something between. So to conclude, I talk about Gemini Interconnect and its uGNI APIs, and also memory pool optimization to improve performance. The details of this talk can be found in this RPDPS paper. Thank you. Question?
If you could add any hardware feature to Gemini to improve the performance for the Charm work you did, what would that hardware feature be, or a set of features?
Okay. So I think currently one thing is like for the middle size message, which is around like 4K, 8K bytes. The performance is still not good because Gemini hardware supports one-sided communication, but Charm is more like a message passing. So we can see it involves actually some extra setup. So I would say that it's one. Another thing is the
hardware, what is the change that you would want there? What would you want the hardware to do for that mid-size message?
It needs something scheme that don't require to know the receiver size memory, because in Charm we don't know that memory.
The reason you cannot use the small message protocol is because there is not enough memory on the other side. So it seems like no amount of hardware will do this, solve that problem, right?
But memory is a problem for the scaling problem, especially when you have multiple cores. So we cannot use too much memories for this purpose.
Right, right. Okay, and you are going to say something else, so I interrupted you. Go ahead and complete your...
Yeah, and also the other thing is the active message. So currently, we still need the completion queue to poll this network. The polling of this completion queue is quite costly. If it has some scheme like, okay, this transaction is done, it can call up some function directly without involving the Charm progress engine to do it. That would be faster.
Not tag is the remote event. So
Yes,
when I set the remote event data,
remote event. So currently we have some limitation of using that one. That one is split to two parts. One part is to recognize the rank of the remote side, and the other is something else. So currently we cannot scale up to 20,000 nodes. That's a problem. Jeff?
So I guess this is sort of more of a comment, but maybe you can respond. So as far as I understand for the hardware, there's two ways one could get around this registration issues. So, and both examples are IBM-based. I apologize to the Cray fan people in the audience. But so BlueGene-P solves this by doing a hardware-based interrupt and then doing a remote get-based rendezvous protocol. So there really isn't the three-way ping-pong. It's just as soon as you fire the interrupt, it's in queued, and then it'll get pulled, so you don't go back and forth. And then the other one, I believe that Perks had, the NIC had the TLB, had a copy of the TLB in the NIC so that it could actually do virtual to physical translation, so that you could do virtual address-based RDMA and then have no registration ever. So, I mean, is that...
Right.
I don't know Perks as well as you guys do, but would both of those things seem like they're a solution?
Right, yeah. Actually, I think MPI also has its own solution of it using some cache memory registration called a uDirect library. So, yeah, currently the memory pool is kind of specific to Charm, since Charm can control all the memories. Yeah, and I don't know the performance of using the virtual memory address instead of, yeah, but that's a solution.
Let's thank our speaker.
Thank you.